the test is tomorrow. Bring your device. And again, the questions that are on the review are a good sampling, but it's not everything that's going to be on the test. So make sure you go through your notes. Make sure you go through, talk to your friends. I know that the study buddy group is happening tonight somewhere, but I don't know. Okay, so number one, it says in general, the atomic mass of elements increases as the atomic number increases. Because again, remember, Mendeleev initially set up his periodic table based on increasing atomic masses, where Moseley came along and said, there's some discrepancies here. There's some things that don't follow the rules where everything in the same column has the same properties. So he said, oh, if I put them in order according to increasing atomic number of protons, then those discrepancies went away. So in general, find the pairs, or a couple pairs at least, on the periodic table where this is the exception. So, and Brock, you said what again? Bi and PO. Bi and PO. So 208.9. Really?
It was on the other thing in the notes.
What are you talking about? Okay. So, I guess so. So, a couple, and I'm not looking for all of them, but there were about 6 or 7 pairs. I think the first one was going from argon 39.95 to potassium 39.1. That was one of them. Another one that a lot of you found was the cobalt to nickel. There again, the mass is going down. You'll get a periodic table tomorrow, and it'll be just like this one that has the group numbers, not like the ones you guys have been using. All right, number 2. Write the symbol for the elements for the following locations. Make sure you know that periods are rows and that the groups or the columns. That's a one-time deal. Make sure you do know your 52 elements, names, and symbols. I may ask you about that. Continuing on. Woo. Looking at number 3. So name the group of elements in the periodic table that have the following outer electron configuration. Again, you need to know 4 of the names. So make sure you know alkali metal, alkali earth, and then jump all the way over to the other side, halogens and noble gases. Those are the 4 you need to know. The other ones are just whatever's at the top, like 4A, 5A, 3A. Okay. If you want to call it oxygen family, nitrogen family, carbon family, great. But just remember, it's multiple choice tomorrow. Yeah, I'm sorry. Go ahead. B? Okay. Oh, okay. Yeah, let me talk about this. So here, what I'm asking or indicating is that we have S2. And if you go 2S2, 3S2, 4S2, etc., it'll actually tell you what column that you're looking at. Here's a better way. Add up the exponent. That'll tell you what group number you're in. So if I had 2 there, then it's in group 2A. What's 2 plus 5? Group 7A. And then 2 plus 6 is 8. So if you see a question like that tomorrow, just add them up and that'll tell you what group. Number 4, how many valence electrons are in the following? So again, whatever column you're in, as long as you're in the A column. Now listen, guys. Whatever column you're in, as long as you're in the A column, that tells you how many valence electrons you have. Okay. So really, it doesn't matter what period you're in or just, yeah. Now, be careful on something like this, okay, where you have the electron configuration. Remember, it's the outermost S and P orbitals. So what I don't want you to do is go, oh, okay, well, I've got 2 plus 2 is 4, 4 plus 5 is 9. There is no group 9A. You're right, because there's only the 2s. Okay, so be careful. That identifies what you're actually looking at. Okay, I think that's fluorine. But what group is it in? Group 7. So it has 7 valence electrons. What happened? You're absolutely right. Questions on 4? Bless you. All right, number 5. Number 5, when it says predict the number of protons and electrons in stable ions, aka most common ion. Okay, so when you see stable ions, think of most common. And I wanted to put that in there just in case I would throw that term at you. So looking at radium, not one of your 52, but it's in group 2A at the very bottom of the column there. It has the number of protons identifies what we're looking at. And again, so since it's in group 2A, its most common ion, or most stable ion, will lose 2 electrons, therefore it will have 86. What will the charge on radium be? +2, good. And then iodine, which is in group 7A, has 53 protons, but it needs 1 more electron to fill up the octet, so it'll have 54 electrons. And its most common charge would be -1. Even though there's multiple charges on the periodic table, I don't want you coming up tomorrow going, what? Why are all those charges on there? Well, probably because you haven't been paying attention for one, but we're not worrying about these charges just yet. Okay, so like with the nitrogen, come on. There we go. So these other charges here, again, ignore those. The only one that we care about is how many electrons do we need to add to get from here to here. Okay, so like nitrogen has how many valence electrons? 5, very good. Okay, 5 valence, not total. So since it has 5 valence electrons, then it needs to add, it already has 5 trying to get to 8, so it's going to add 1, 2, 3 more. Okay. So 4A, we're not touching that, that's AP. Because it could go either way. That's why with the carbon it could either be +4 or -4. Yeah, we're going to stay away from that because there's too much that can go on there. Yeah. Okay, so does that make sense? Better understanding there. The common stable ion may have thrown some of you off on that. RA, but it's not one of our 52, so we don't care about it tomorrow. So make sure you know your 52. Sorry. Correct. Just fun trivia. All right, number 6, predict the common ions. So here again, this will be a common type of question that I could ask. So common ions formed, which means, again, it follows that how many valence electrons do we have? If we have 3 or less, what are we going to do? Lose, very good. You're going to lose electrons so that you have 0 valence. Okay. So if it has 3 or less valence electrons, lose them so you have no valence electrons. That's how we get our positive charge. If you have 5 or more, okay, again, what are you going to do? You're going to gain. You're going to gain electrons until we have how many? 8, or our octet, so to speak. Okay, so 8 electrons. Gain to get 8. And that's why we stay away from group 4, because that one can go either way. It'll disappear. Yeah. When you watch the video, you won't see that line. Yeah. That's why I have this post-it note here to remind me not to write in that area when I can't see the box. That's my cheat. Oh, so looking at these, does everybody understand why I have the charges that we have? Somewhat. Okay, good. That's better than I have no idea. And then, again, make sure that we're going to our nearest noble gas. So if you're gaining electrons, you're going to move to the right. If you're losing electrons, you're going to move to the left and go up and then slide all the way to the right. Okay. All right. I love these questions. And you will too, because you're going to see a couple of them tomorrow. And it'll be worded differently. And again, it's all about the ionization energies, being able to determine who are my core electrons and who are my valence. So number 7 says the first 3 ionization energies of an element in kilojoules per mole, don't worry about the units, we have IE1 that's 403, then we have 2632, and then 3859. Question is, what is the charge on the most common ion of this element? How many valence electrons does this element have? And identify the element from the list. So the key here is we're looking for that big jump that's over 400% in energy. So remember that the first electron is always going to be easy to remove. First one's always going to be easy. It's when we go between elements that we're trying to find where's the big jump. So going from the first ionization energy to the second ionization energy, do we have an increase of over 400%? Yeah. So that is the big jump. That's telling us that from here to here, we're actually pulling core electrons out of that second attempt, so to speak. So in this case, it has one valence electron, and so that means it's in group what? If it has one valence electron, it's in group what? 1A. Good. Or alkali metals. So however many electrons are easy to remove, that's what column it's in. A respectively. Okay. So, and if the big jump would have happened between these two, use your imagination. Let's say that it's not 26, but it goes from 400 to say 600, then what would our option be here? What was I thought I heard somebody say? 2A, which element would it be then? Barium, because that's the only element represented in group 2A. Okay. Yeah, don't forget the names. And I think we have a couple more type questions like this. So since one is easy, it's a valence electron. One valence electron has a +1 charge, and of this group, it's rubidium. Isn't that fun? All right, number 8, use the position on a periodic table to determine the number of d orbital electrons. And again, don't forget, from this point forward, or actually from a couple days ago, if we can fill up the d orbitals all the way or halfway, we're going to move electrons from the s to the d. So for iron, if I look at iron, let's look at iron real quick. Do a little iron up here. Where are you? Table. So looking at iron, okay, iron is right here. So if I look at how many d orbital electrons we have 1, 2, 3, 4, 5, 6. So is it possible for me to move these two electrons over to either have iron half filled or fill it up? No. Very good. Because we would need at least 4 more electrons, so it doesn't make sense to move any electrons over. Here's another thing that you cannot do. You can't say, well, you know, there's 6 of those there. Let's just move one over to the P. Don't even think about it. Because what you're doing is you're moving from a lower energy level to a higher energy level, and we just don't move electrons forward on their own. Unless we are going from a higher energy level, in this case we're going from a 4s orbital to a 3d orbital, if we can fill up the d's halfway or all the way. And since we're beyond the halfway point for iron, it doesn't make sense. What was the next element on the list? Zinc? Okay, good. So zinc, yeah, it's already filled up. So, I mean, you can't move any electrons over. So, in this case, how many d orbital electrons do we have represented? 10. Good. I didn't answer it for the iron, but how many iron d orbital electrons? 6. Good. Now, chromium, okay, we can move an electron from the s, one of these, over so we can have a half-filled d. So we'll have, sorry, wrong way. So 3d5 in that case, where this would be a 4s1. Okay. So if you can move one or both of the s orbital electrons, either have that or this, or actually, let's not just say 3d. So if you can have, say, a d5 or a d10 by moving one or both electrons, we're going to do it. Okay? If we don't get half or full, don't mess with it. Okay? Don't get creative. This is an art class. So we have very strict rules and guidelines here. That's right. That's life. Okay? So again, iron has 6, zinc has 10, chromium has 5. Which kind of segues into the next question. Did you find your device? Perfect. 6. Yeah. All right, looking at number 9, what element has electron configuration? Now, looking at A, you have 4s2, 3d2. So again, we can't move any electrons forward to half fill of the d, so leave it as is. And here's an easy way to do this. 2 plus 2 is what? That's my advanced class there. There we go. So we got 4. Whoop, no, sorry. So if we look at it and you say, okay, well, I've got 4, then just count over. 1, 2, 3, 4. Okay? And that's your element. Now, in the next case where we have chromium, where it has this scenario, and it's 4s1, 3d5, do the same thing. What is 1 plus 5? 6. 1, 2, 3, 4, 5, 6. Okay? Now, what I don't want you to do is simply go, well, it's 3d5, so I just count over 5. This ain't full. Okay? You can't just count over and say it's manganese. Count how many total you have in that row. Okay? You can make this really easy or very difficult. Don't make it difficult. Remember, this is just chemistry. It's not difficult. You guys make it difficult. Yeah, it's not. Calculus is easy. It is not rocket science. You're right. You're right. All right, number 10. Which transition metal, scandium with a +3 or zinc with a +2, is isoelectronic with argon? Now, what the heck does isoelectronic mean again? Same number of electrons. That's it. Okay. So again, isoelectronic means you have the same number of electrons and or same electron configuration. Tomato, tomato. Okay. So if we're looking at scandium with a +3 charge, okay, how many electrons did scandium lose? That's +3 charge, so it loses 3. So it started off with 21 electrons. How many does it have after it loses 3? 18. Which would happen to be the same number as argon. Okay? If I look at, and again, not rocket science, if I look at zinc, and zinc has a +2 charge, how many electrons did it lose? 2. So how many electrons does it have remaining? 28, which is not 18. I know. Not today. I know. Hopefully not tomorrow either. But I don't know what tomorrow holds. Oh, I've got the test ready. Hunter, you can do it right now. Let's get you going on that test. Hey, I'm only giving them 10. All right.
You're only giving us 10 minutes.
That's all you need. 5 questions per minute. You either know or you don't, right? Celeste. Could what? Up this way? Okay. What did I say? Did my job well. Don't jump. Good, Cameron? All right. Number 11. For which of the following elements do you expect there to be a very large increase going from the second ionization energy to the third? So here's how we translate this question. Where is the big jump between the first and the second electron, the second and the third and the fourth? Where's the big jump? Second, third. There's a very large increase going from the second to the third. So how many electrons are easy to remove? 2. Very good. So if there's a very large increase, so it's kind of like we're doing the IE. Okay, so, and if you see a question like this tomorrow and you're like, oh my goodness, what should I do? Make up some numbers. Just go, okay, well that's 200, that's 400. Let's make this at least 4 times greater. Let's go 3,000. That's at least 4 times. Okay, so you have that visually in front of you, and then you can say to yourself, well, self, if I go from here to here, okay, That's only a doubling here to here. Ooh, there's a big jump. So that means that 2 of these electrons are easy to remove. This is coming from where? The core. Very good. So in that case, knowing that the 3rd electron is being attempted to be pulled from the core, then we have a what charge? +2. So we have to look at an element that's in group 2A. Everybody good? Okay. All right, number 12. What trend is observed for the following atomic radius of atoms? So moving down the column, what's going to happen? Bigger. Okay, it doesn't matter if it's neutral or ionic. Regardless, it's going to get larger. The reason is because we're adding electrons to orbitals of different energy levels. So as you fill up this energy level and then move on to this one, we get bigger. Move on to the next one, we get bigger. Okay, which is different than moving left to right along the periodic table. So when you look at your periodic table and you say to yourself, he said they get bigger as we add electrons. What I don't want you to do is say to yourself, well, wait a minute. If we are adding electrons from here to here, we're not adding electrons to the same atom. Okay? That is true. That's the ionic way to look at it. The trend is as I go from lithium to beryllium, beryllium's smaller than lithium. Going from beryllium to boron, boron is smaller than beryllium because we're getting closer to 8. Now, again, in AP, we're going to talk about Coulombic attractions, effective nuclear charge, Zeph, all those fun things to explain this. This you can comprehend right now, hopefully. Hopefully. Yeah. All right. Number 13, we're not talking about shielding. 14, another ionization question. Oh, yeah. So number 14, what is ionization energy? I think I removed that part out. Is that true? Okay, sorry. So again, ionization energy, that was the question you had on the homework last night. Ionization energy is the amount of energy needed to remove an electron. The trend, as you move left to right along the periodic table, what happens to the ionization energy? Bigger. Good. Because those elements on the right side of the periodic table, non-metals, they don't want to give away their electrons. Metals, they want to. All right. Ooh, I like this one. Why does sodium have a higher second ionization energy than first?
Is that when they're like removing?
Okay, what? I heard Celeste. What did you say, Hunter?
I said, is that like when they start to remove electrons?
Yes. So, how many valence electrons does sodium have? How many? Oh, come on. 1. Very good. So, the reason why it has a higher second is because we're pulling from the rows above or the core electrons. Good. I think that's the 3rd or 4th ionization question we've had. Ooh, number 16. I like this one. Remember, if you have more protons than electrons, okay, again, if you have more protons than electrons, are you big or small? Small. If you have more electrons than protons, are you big or small? You're big. Okay. So here's the question. It's asking which has a larger radius. So sodium +1 or neon? Which one has more electrons? Neither. They have both 10 electrons. Okay. So they both have the same number of electrons. Which one has more protons? Sodium with 11 protons, where neon has how many protons? 10. Sorry.
Did you just say that both of them?
Put what I just said. Okay. So which one? They both have 10 electrons.
Wait.
Go ahead. Again, protons identify what we're looking at. So just because it has a +1 doesn't change the proton number.
Oh, that's Na plus 1 and Ne. I was so confused. I thought it was Ne plus 1 and Ne. And then I was like, but the protons have...
Yeah. All right, so in this case, since we have more protons than we do electrons, this one is smaller.
No, that makes sense. I just thought they were both Ne, and I got real confused.
Well, there you go.
Protons being different things.
Yeah. What's happening? Okay, so again, these both have 10 electrons. So they both have the same number of negative charges. Sodium lost one. It had 11. Now it only has 10. And then the sodium has 11 positive charges in the middle, where neon only has 10 positive charges in the middle. So if you have more positive charges than negative charges, your radius is going to be smaller. If you have more electrons than you do protons, then it'll be larger. If you're comparing equal number of protons and electrons to somebody that has more protons than electrons, and they're the same number of electrons, then that one's smaller. So the more positive charge will draw that in. Yep. More electrons is bigger. If we had that scenario. Now, the majority of the questions tomorrow will be like, what is that, number 18? Yeah. So. Note of 37. What trend in the ionic radius of an element would you predict as you move down the family? Same as atomic. As you add more energy levels, you're adding orbitals with electrons. Okay. And is this our... Nope, we're not done yet. This is more of what you'll be asked tomorrow. Okay. Looking at the same type of elements, whichever one's more negative is bigger. Whichever one's more positive is smaller. Okay? Questions about that? So again, it goes back to the more electrons, proton deal. And then last but not least, and I do apologize for the electron configuration for molybdenum. It should have been 5s145. Yes. What's that? Okay.
Wait, it's supposed to be 48.
Should be 5s145.
Okay, because I was like, I still got FL. What are you talking about?
All right. All right, so again, bring your devices tomorrow. Have a good night.